So the first topic we talk about in Unit 2 is dealing with limits. And we're going to be doing a lot with limits in Unit 2 because they're going to help us to deal with what we eventually will call a derivative. Now, if you're given a function, and the way the limit notation looks is that that function you have being pictured down there is basically saying that the limit of a particular function f of x. Now, sometimes you can use f of x, but oftentimes you're going to find the actual expression that f of x is equal to, the algebraic expression. So unless it gets really complicated, then sometimes you'll be given f of x equals the complicated function and then the limit. But this is basically saying as x approaches 3, the value of f of x equals 10. So basically, if I was looking at the graph, as x gets closer and closer to 3, I would expect the y value to get closer and closer to 10. So that's how a limit is kind of, the notation is demonstrated. And that's what you're kind of seeing here. For example, we're seeing here, they're breaking it down a little bit more. As I approach from the left, which is indicated by this notation up here, give me a second here. If I'm approaching from the left, that's the notation, because the x value is approaching from the left-hand side. If I approach from the right, that's this notation here. When I don't see the little superscript with a plus or minus, that means I'm approaching from both sides. So x is getting closer and closer to 3 in this breakdown, and we saw that the y was approaching 10. So, and that's what they're telling you here is basically a breakdown. As x approaches c, that means from both sides. When you see one side of the limit, you're going to see the little minus and plus in the superscript area, kind of indicating that you're approaching from that particular side. Therefore, the limit as x approaches c of f of x is sometimes called a two-sided limit, as I kind of mentioned before. So now, how do we evaluate these limits? Because sometimes, and the whole premise behind it is I can have functions approach a value as x gets closer and closer to another value, but I don't necessarily have to actually reach that value. It could be some sort of asymptote, it could be a hole. There's all sorts of things that, the limit can approach a value, but actually never really reach it. And the first thing I always do when I evaluate a limit is that I basically evaluate the function at that value. So we do a direct substitution for the limits, and they give you some additional limit rules down here. So basically, if I substitute the number that x or whatever the variable is I'm using in that particular limit is approaching that number, I substitute that number in, and if I get a numerical answer, that's it. I'm done. Now, a lot of times that's not going to be the case, and depending on what happens as a result of that is how I choose to handle it after that. But that's always the first thing I should always do is put the number that x is approaching, or whatever the variable is. A lot of times it is x, but it's not always. And then, see what happens. If the answer is a number, I'm done. If not, I have to look at the situation and evaluate accordingly. So for this first example here, all I'm doing is I'm looking at the function, and because the limit has x approaching, in this case 4, I'm just simply going to substitute it in. So I get the square root of 4, and the square root of 4 is, of course, 2. So by the rule we just talked about, that's what the limit equals. Same thing if I do the limit as x approaches 6 of x squared over x plus 3. I substitute the 6 in for the x, and I get that the limit equals 36 over 9, which is just 4. So again, by this general arrangement, that's what I expect the final answer to be in both cases. Now for this limit that you were asked to try, again, this is the very basic start of a limit, and the very first thing you should always do is to substitute the number that x is approaching into the function, into the expression. So I'm just going to replace all the x's in that expression with a 4, and I'm going to simplify and evaluate, and I get 0 over 5, which is just 0. So the limit as x approaches 4 is just equal to 0. In the previous court recording, in the example 1, we dealt with the very first step that you would have if you're doing a limit. And that is you attempt to substitute the number that x or whatever your variable is approaching and see if you get a numerical value. Now, a lot of the circumstances that we focus on in calculus, whether it's business calculus or scientific calculus, is situations where that just simply does not work. And if you look at this next example that I'm going to ask you to try, it is a circumstance that something different is going to happen, and sometimes a lot of students overlook it. But let's have you give this next one a try and see what you think needs to be done to solve this limit. In this circumstance here, we still do our very first step. We take the number that x is approaching, in this case it's 5, and we substitute it in. And a lot of students misinterpret what goes on here, so let's have a look and see what actually does happen and how students often misinterpret it. So in this case here, I plug the numbers in for x, and as a result of that, I simplify it, and I get 0 over 0. Now the problem is a lot of students misinterpret how that is to be viewed. A lot of students will simply say that that is 0. Well, it isn't. 0 divided by 0, if you're following one rule of mathematics, yeah, 0 divided by a number should be 0. But the problem is we have two other rules of math that are in conflict. We have a rule that says you're not allowed to have a denominator of 0 simply because of the fact that a denominator of 0 means that we're getting a really infinitely big result. And, infinity is not a quantity that is defined, so this would be having a 0 denominator is often typically stated as being undefined. We also have a rule in mathematics that says anytime I divide a number by itself, it's supposed to equal 1. So we have 3 different rules of math that would interpret this particular fraction in 3 different ways. And because of that, that's an indication that we have what we call an indeterminate form. An indeterminate form often is the result of me getting a result that puts several different rules of mathematics in conflict with each other. So anytime that I get the 0 over 0 indeterminate form, because there are others that exist, we're not necessarily going to study those too much, but they might appear later. Right now, this is really what we're going to focus most of our attention on. Usually when you see this show up, it means that you have more work to do. And as the example 2 here's subheading is finding limits by simplifying, that's typically what you're going to need to try to do in order to evaluate the limit, is that you're going to be looking to simplify your f of x, your function expression, and then try to go back and use the rule of substituting the number back in. So let's see how we would go about doing that. So if I take the limit as x approaches 5, and I already know it equals 0 over 0, I'm going to look to, one of the best ways of simplifying is to factor. And what I'm going to do is I'm going to factor both the numerator and the denominator. If I factor the numerator, I get x minus 5 and x minus 2. If I multiply those through, I would get the x squared minus 7x plus 10. On the bottom, I do have a difference of squares, and that's one of those instances that, should be an easy factoring for you because the difference of squares always factors into two conjugates. And, we're basically, I have x, I have the same constant in the last position. The only thing that's different is one has a plus and one has a minus sign. And the reason why I do this, and the reason why it's important for me to do that, is I need to figure out what's going to essentially simplify. And when I simplify this, I can see the top and bottom both now have a multiplication of x minus 5. And because of that, and the rules of division, I can cancel out that x minus 5 from the top and bottom. So now my limit is actually, as x approaches 5, of x minus 2 over x plus 5. So I simplified the expression, and once I simplify, I go back to step 1. I'm just going to substitute the number into the expression. So I'm going to substitute 5 in for all the x's again. In this case here, I get 5 minus 2 on top, 5 plus 5 on the bottom, which becomes 3/10. So the actual value of this limit is 3/10. Typically when you get the 0 over 0 circumstance, because when they talk about continuity and things in the textbook, this is an indication that if I end up with 0 over 0 in the beginning and end up with a number after I simplify, that's an indication that the particular function, the f of x, if I graph it, I would have a hole there. So there would be a hole at this function at the coordinates 5, 3/10. So that's the end of example 2. In the previous two examples, primarily with example 2, I had made mention of prospects of dealing with infinity. And some of which you have to be able to interpret are limits that involve infinity, either situations where x is approaching infinity or negative infinity, which means it's going on forever and either to the right or to the left, or situations where the value f of x is approaching infinity and how those are interpreted and seen in various circumstances. So let's have a look at this function here. And with all typical rational functions, if you remember any explorations you may have done in previous algebra courses and things of that nature, rational functions often have horizontal and vertical asymptote. Sometimes they might have what they call an oblique asymptote instead of a horizontal asymptote, which a lot of times when you were studying it was a slanted line. Well, how are these interpreted with limits? So there's two types of limits involving infinity. There's situations where x is approaching negative infinity or infinity. And so when I look at this circumstance here, if x is approaching negative infinity, we can see that f of x, the graph, is approaching this value of 3. It's going to be a circumstance where it's approaching that value but never quite reaching it. So we can see here, just by the graphical interpretation, as x approaches negative infinity, here it's going to equal 3. And the same thing happens with this particular graph as x approaches positive infinity. F of x is also going to approach 3. When you see this kind of behavior, when x is approaching a value involving infinity, whether it's infinity or negative infinity, and it's equaling a numeric value, that's the indication that you have a horizontal asymptote, and that's how it's interpreted using limits. So these two limits show that f of x has a horizontal asymptote of y equals 3, on both the left and right ends. There are some functions that sometimes will have a different horizontal asymptote on one side than another, but those tend to be piecewise functions, and we're not going to be worried too much about that at this point. Now, other circumstances are, okay, a situation like this. We can see we have a vertical asymptote of x equals 2. And I can see here that as f of x as x approaches 2 from the left-hand side, f of x approaches negative infinity, which means, as I get closer and closer to 2 from the left, I expect the y value to become ever more negative and, just bigger quantity-wise, but very negative at that point. As I approach 2 from the right-hand side, I can see that f of x is approaching an infinitely big number and positive, so it's approaching infinity. Now, in this circumstance here, because the left-hand limit and the right-hand limit don't agree, and anytime that left-hand and right-hand limits don't agree, that means that the limit does not exist. Okay, but because the two original, the left-hand and right-hand limits involved something dealing with infinity, that indicates that I have a vertical asymptote at that particular x value. So I don't have to have a graph in front of me to be able to interpret what's going on a graph. If x is approaching infinity or negative infinity and I'm getting a number, that indicates a horizontal asymptote. If I am approaching a particular number and I'm getting values for my limits that are involving infinity or negative infinity, that means I'm dealing with a vertical asymptote at that point. If the left-hand and right-hand limits don't agree, then the limit does not exist, but I can still have a vertical asymptote. So this is kind of a summary, and this is from your textbook of what kind of things are going on, dealing with what we just talked about, limits involving infinity that they expect you to be able to know about. So let's have you have a look at interpreting another function using limits to identify what's going on in the function. So you were given this function f of x equals 2x plus 1 over x minus 1, and you were asked to determine the following limits, although determine there is kind of misspelled, but be it as it may. So the first one I'm looking to do is the limit of f of x as x approaches infinity. Well, how do I interpret that? I mean, I don't have a graph in front of me. How do I deal with that? The way I deal with an x approaching infinity or negative infinity is, for me to evaluate what's going on, what I often do in a rational function is I divide both the numerator and the denominator by the highest power of x. So what you're seeing here is I look at the numerator and denominator and see that the highest power of x is x. So I divide the numerator and denominator by x. Now, since I'm doing the same thing to the numerator and the denominator, the overall effect is essentially me basically dividing by 1. And dividing by 1 doesn't change anything. Now, what this allows me to do is when I simplify this, I get the limit as x approaches infinity of 2 plus 1 over x over 1 minus 1 over x. Anytime that I have a number over x and x is approaching infinity, which means that the denominator is getting infinitely big, then that fraction is going to get infinitely small and approach the value of 0. It's not going to be 0. 1 divided by a number is never going to be 0, but if I get a really huge number in the denominator, and I'm taking 1 or any number on top and dividing it by a really huge number, the result is a very, very small result. Practically nothing, depending on how big x is. So since it is a limit, the value of 1 over x in both of these cases as x approaches infinity becomes 0, which means that this limit becomes 2 over 1, which is 2. The same thing happens for b. As I approach negative infinity, I do the exact same thing, and I get the exact same result. It's approaching 2. So a and b together are essentially telling me that I'm going to have a horizontal asymptote at y equals 2. When I look at the limit as x approaches 1, now when I put 1 into this function, I can see that 1 is a domain restriction. It's going to make the bottom 0. And the top is going to be 3. So if I end up with a number over 0, that usually tells me I'm going to be dealing with some sort of vertical asymptote. I still want to know what the behavior of the graph is. Because sometimes a vertical asymptote, I can have both the left-hand and right-hand sides approach either infinity or negative infinity, both the same value, or they could go in opposite directions like we saw in the previous graph. I got to be able to determine that based off of what's going here. So when I look at this one here, if I approach 1 from the left-hand side, that means x is slightly smaller than 1. And if x is smaller than 1 and I'm subtracting 1 from it, the bottom is going to become negative. So I end up with 3 over a negative value, which is going to be negative, which tells me that, since this is going to involve something dealing with infinity, this is going to equal negative infinity. So I know the limit as x approaches 1 from the left is going to be negative infinity. When I approach 1 from the right, very similar circumstance. I'm still going to have a 0 on the bottom, a 3 on top. What's going to be different now is that since x is slightly bigger than 1, when I subtract 1 from it, I'm going to get a positive result. And therefore, 3 divided by a positive number is going to be positive. So no matter what I make x equal to, I'm going to get an infinitely big number down in the denominator. It's going to be positive, so I would expect this to go to positive infinity. Because I'm getting these indicate I do have vertical asymptotes. This means that I'm going to go down forever as I approach 1 from the left. I'm going to go up forever as I approach 1 from the right. But the limit of f of x as x approaches 1 itself, since it's indicating a two-sided limit, that's not going to exist because my left-hand and right-hand limits did not agree with one another. And anytime I'm dealing with a limit involving infinity, where x is going to where I'm going to put a denominator of 0 into the limit as I evaluate it, it's going to be a situation where I have to look at the left-hand and right-hand limits, unless I'm already aware that I'm only doing one of those to begin with. One of the things that we study making use of limits and evaluating functions is to determine the continuity of a graph or a function, determine if it's continuous at a specific value or whether or not it's continuous across all values, all real numbers, or just continuous across its domain, which are circumstances that you're going to often be asked about. Now, basically, we looked for specific issues to determine if there's any possible points of discontinuity. I mean, polynomial functions, linear functions, they typically are going to be continuous everywhere. It's when we start looking at rational functions where I have domain restrictions. If I look at anything involving a square root symbol in my function, as long as the variable's underneath the square root, I deal with circumstances that certain x values won't work. Anything where my domain might be restricted in some way also tends to cause there to be issues potentially with whether or not the function is continuous. Also, when I deal with piecewise functions, it's another circumstance where I tend to be looking at possibilities of functions being discontinuous at specific points or values of x for that function. So a function is said to be continuous if its graph passes through the point at x equals c without a hole or a jump. Or basically, without any kind of domain restriction or any kind of break between one graph to the other. So they kind of show you what that is down there. Now, a hole is what they sometimes would call a jump discontinuity, and most textbooks would tend to call a hole a removable discontinuity, whereas a jump at a particular value, also in other books called a break, is another type of discontinuity. And limits can oftentimes help me figure out if I have one or the other, or neither. So let's have a better look at this with more clarity. So basically, I run a test to see if a function is continuous. If there's any point where I think it may not be continuous, anything that seems out of the ordinary, anything that might be causing a domain restriction, if it's a piecewise function, any value of x where I go from one formula to the next, those are the ones I tend to try out. And what I do is I look to see if it passes this test to see that does the limit as x approaches that particular value for the function equal the same thing as f of c, just basically the same thing as me substituting into the value. So it's kind of like me running that first test for limits. All those functions that we dealt with originally, for the value, at least for the value of x we were looking at, were continuous at that particular point. And if it's continuous there, then we know that the function exists and everything like that. And so when we had discontinuities is when we get those indeterminate forms, when we get a number over 0 where I could have a vertical asymptote. if I have a piecewise function, where the x value, you know, works for one function, one formula for the function, and then x values that follow that, use another formula. Those are all potential areas of discontinuity. So I run this test on it to essentially try it out to see if I do in fact have a function that is continuous. So the three things I'm going to look for when I determine continuity is, first of all, I want to make sure that f of c is defined. If I have a situation where the limit exists for a function at a value c, but f of c itself does not exist, that's usually the indication of a hole. If f of x as x approaches c does not exist, that's often the case of either having an infinite discontinuity, which means that it's a vertical asymptote, or I have a break, and it really depends on what I see in the function as I work with it. And then, of course, the last one is that those two have to agree with each other. If I get f of c to be one thing, and the limit as x approaches c of f of x to be another thing, that's another type of hole. That's what we tend to call a jump, because we have a hole with a dot somewhere else. So, so let's have a look at an example. So this says example 8 here. This is coming from your textbook, so I'm just using that as a guide. These are the types of functions that you can sometimes see. So, these are areas where these are discontinuous. At C, if I just have a hole there, it's not defined there, so it's not continuous. If I have an entire break, or if I just have a in there, so the limit as x approaches c from the left and from the right are different, and f of c itself is different from those two. That's the limit not existing, and f of c being different than either one of those two. And the third one is showing me an instance where the limit as x approaches c exists, but f of c itself is something different. These are all areas of discontinuity. So which functions are continuous? Linear quadratic functions are continuous. So are all polynomial functions. Along with that, as long as I have integer powers of x with coefficients in front of them, I'm good. And as long as the coefficients are all usually integers and rational numbers are good, then we have no issues there either. Exponential functions are continuous, and logarithmic functions are continuous on their domains. And that's the thing about them, is that they're continuous on their domains. Exponential functions, the domain's all real numbers. Logarithmic functions, they're not continuous for all real numbers. They are continuous on their domain. So any value of x that I'm able to put into the function and then evaluate a logarithm of it. And we're going to talk about logarithms more as this course progresses. Then everywhere it's going to be continuous on that domain. Anything else, it's not going to exist. So some rules about continuous functions. If f of x and g of x are continuous functions, then me adding or subtracting them to form yet another function, that would be continuous. A constant times one of those would be continuous. If I multiply the two functions together, they would be continuous. If I divide the function, that's a little shaky, as long as for the particular value of c, that g of x is not equal to 0 at c, then it would also be a continuous function. And if I do a composition, I would expect that to be a continuous function as well. As it says down there, every polynomial function is continuous. That's one of the things I talked about before. Every rational function is continuous except where the denominator is 0. And that's an example we mean by continuous on its domain, because any value that makes the denominator 0 would not be on the domain of that function. So that's the difference between being continuous, and if that's all I say, that means all real numbers is understood. And then continuous on its domain means, okay, well, anything but the one point where it's not defined. So this example that you were asked to do, you were asked to determine if the following function was continuous at x equals 3. So let's have a look at this. Now, if x equals 3, then I end up with 0 over 0 on this. And 0 over 0 is an indeterminate form. So I can answer the question more or less right now that it's not going to be continuous there, because that sign there tells me I have an indeterminate form. That means it's going to have a point of discontinuity. But the question you were asked had choices that wanted you to identify the type of discontinuity you had. 0 over 0 often means you are going to have a hole, but it's not a guarantee. There's other things you could get in that circumstance. And more work has to be done before you can make that conclusion. You have to verify that after I simplify to get rid of the indeterminate form, I do end up with an actual number for that limit, and that will tell me I have a hole. If I end up getting something else like a number over 0, that would indicate that I would have a vertical asymptote, and I had to do a little more exploration there as well. So there's different things that could happen. I just can't assume that automatically I get 0 over 0 that it's going to be a hole automatically. So let's simplify f of x. So I do factor the bottom because it is a difference of squares, and that should be an easier factoring because it had a very specific rule for that, whereas other factorizations of quadratics, that can be tricky at times, especially depending on what your b and c values were in your expression. Or if you had a leading coefficient that was other than 1, that would often complicate things a bit too. So the bottom does factor in x minus 3 and x plus 3, and essentially I do have a 1 being multiplied in front right here. So I'm going to keep that in mind because now the top and bottom have a multiplication of x minus 3. So, using the methodology I used before, they're going to cancel, and therefore I'm going to end up with the 1 on top, the x plus 3 on the bottom, and that cancellation should make the indeterminate form of 0 over 0 also vanish. Once I've established that, I go back to step 1 again. I'm going to substitute the value of x, in this case 3, in for x, and see what I get. And what I get in this instance is that this limit is going to equal 1/6. So since I do get this to equal a value, that means that I do have a hole at 3, 1/6. So the function is not continuous at x equals 3 because of the existence of a hole at 3, 1/6. However, if I were to go back and say, okay, well, is it continuous on its domain? Since x being 3 or negative 3, if I would state, okay, what's the domain? I would basically say something along the lines that x is not equal to 3 and x is not equal to negative 3. That's part of the domain. And since the domain, here, is going to exclude that, that means that, well, that's not part of the domain. Therefore, I would still say, okay, well, it's continuous on its domain since x equals 3 is not part of that domain. Or, at least it's so far from what I'm looked at. When I explore the x equals negative 3, though, I would probably find out as I go through more of it that I do have a vertical asymptote, which would mean it's not going to be, continuous on its entire domain because of the fact that at negative 3 I'm going to have another issue with a vertical asymptote, and that's not going to be able to be removed. And that's why you're going to see some textbooks refer to a hole as a removable discontinuity, because if it's not part of the domain, that particular x value, that means that the discontinuity, the hole, is essentially removed, and therefore it's continuous across its domain. As we had discussed in the recording for example 4, there is a difference between being continuous for all real numbers and continuous on its domain. In some cases it does mean the same thing. In other cases it does not. And we had a brief discussion about the function f of x equals x minus 3 over x squared minus 9. And although I was focusing my attention as to what happens at x equals 3, if that was the only domain restriction if that was the only issue I had, which is it was a hole at that point, I would say it's continuous on its domain based off of that. With further exploration, if I also looked at x equaling negative 3 on that last example, that was an indication that I would probably find a vertical asymptote, which means it would be discontinuous on its domain because of that. So here, when I'm asked if it's continuous on its domain, first I have to determine what its domain needs to be. Secondly, I have to determine, well, what possible types of discontinuities I'm going to have, because, I can't take every single x value in a domain and test it. I would never get done because there's an infinite number of values oftentimes in most domains of functions, so I would never be able to get done with that. So I have to be able to focus my attention and recognize where possible discontinuities would be and be able to assume that everywhere else it's continuous. So as you look to do this example, and I'm going to pose this question to you, answer whether or not this function is continuous on its domain. I want you to answer the question, but I want you to determine, well, first of all, what values of x am I going to try out? How am I going to determine if it's continuous or not? And then, based off of that, be able to answer the question. So I'm now going to turn it over to you. So, as I said before, I cannot test every possible value of x on its domain, because theoretically the domain here, since x's can be anything less than or equal to 2, so if I look at a number line, I mean, here's 2, here's 6. The first line says anything that's 2 or less. Okay. Anything that's between 2 and 6, since 2 was already included beforehand, and it's on the domain. So I would get there. And then the last line says anything valued more than 6 or equal to it. So I'm filling in the entire number line. So basically the domain for this function is all real numbers. So I do have to go into more exploration here and figure out, well, where could it possibly be discontinuous? Because I'm not going to be able to show it's continuous for every single number in the real number system because it's an infinitely big system. So the very first thing I do is I look at, this is a piecewise function made up of these 3 pieces. This one here is quadratic. Now, at face value, quadratic functions don't have any domain restrictions, so I wouldn't expect this quadratic function to have any values of x where it would cause a discontinuity. Therefore, I don't have to worry about that. These 2 are linear. Same issue. I mean, they're continuous everywhere, so the functions themselves are not going to cause me any kind of concern because of the fact that these functions would normally be continuous everywhere. Where I'm going to have potential issues are when x equals 2 and x equals 6, because since I'm going from one formula to the next in both of these circumstances, that's where I'm going to have a potential break in the graph. And if the graph does break, that would be a point of discontinuity. So I'm going to look at an instance where x equals 2, and I'm going to check also what happens when x equals 6. I'm going to do x equals 2 on this one. So the first thing I'm going to do is say, okay, well, does f of 2 exist? If it doesn't exist, that would be an issue. Well, if x equals 2, then I'm following the first line. I have a lot of, let me erase some of this and just start that part over again because of the fact I have a lot of stuff here. I'm going to look at x equals 2 here. So f of 2 doesn't exist. Well, if I'm following this piecewise function, f of 2 would be 2 squared, because values that are 2 or less, I would follow the first formula. That equals 4. So it exists. So now, since I'm using one function as I approach from the left, so this would be approaching from the left up here, values that are smaller than 2. This would be approaching from the right up here. I want to see if those two limits, agree with each other. And if they do, and they both equal f of 2, then I'm continuous. So I'm going to do the limit as x approaches 2 from the left of f of x, which means I'm going to do the limit as x approaches 2 from the left of x squared. And with any other limit, I plug the number in first to see what happens. That gives me 2 squared, which is 4. So that exists. The limit as x approaches 2 from the right of f of x. Well, for this formula, I'm going to be using, instead of x squared, since I am approaching from the right, I'm going to be using the formula 6 minus x, which is 6 minus 2, which equals 4. So I know the limit as x approaches 2 from both sides of f of x equals 4. And we also know that that's equal to f of 2. So because of that, I know it's continuous at x equals 2. So if 2 was the only point of possible discontinuity, I would say, well, that's not an issue. It's continuous there, so I would say the function's continuous at that point. But I also have to try out what happens at 6. So let's see what happens there. At x equals 6, first I have to see, does f of 6 exist? Well, if I follow this function here, I'm going to be using the formula 2 times 6 minus 17, which is 12 minus 17, which is negative 5. So f of 6 does exist, so we're good there. But again, since we go from one formula to the next at 6, I wanted to see if the limit would exist. So the limit as x approaches 6 from the left of f of x is going to be the limit as x approaches 6 from the left of 6 minus x. And again, like any other limit, I'm just going to plug the value in. That's going to give me 6 minus 6, which is 0. So I know the limit as x approaches 6 from the negative side, or the left-hand side, is going to be 0. When I do the right-hand limit, again, since I'm falling from the right-hand side, I'm going to be following the formula 2x minus 17, which means I'm just going to plug that in. But the thing is, and here's the issue, the limit, since the left-hand and right-hand limits don't agree, as I approach 6 of f of x, this doesn't exist. Even though f of 6 and this agree with each other, the fact that the left-hand limit doesn't agree with those three means I'm going to have a break. It's going to be a break, so it's discontinuous. At x equals 6, it's going to have a break there. And I can tell that because of the way that the left and right-hand limit don't agree with each other. So is it continuous on its domain? The answer is a big, resounding no. So why do we study all these limits that we've been talking about in the previous 5 examples? The reason we study these limits is because we make use of them as we look to study the difference between average and instantaneous rates of change. Now, a rate of change is like things like velocity, or as I mentioned here, the temperature is increasing at a rate of 3 degrees per hour, or falling at a rate of 2 degrees per hour, whatever the case may be. So as I go through this example here, they're taking the function f of x equals x squared to represent the number of degrees that the temperature is on a given day, or whatever the case may be, when x is in hours. And we want to calculate the average rate of change over various time intervals. So what they're showing here is like, how they would go about doing that. And so, at time 1, it's 1 degree. At time 3, it's 9 degrees. So they're showing here, like, if I want to do the average rate of change from time of 1 and 3, whichever those are over the course of 2 hours, that hour 1 and hour 3, then, I would look to see that the average rate of change they calculated is 4, and that would be degrees per hour. So basically, that means that between those 2 time points, on average, the temperature was increasing 4 degrees each hour. When I look at, then they break it down further, say, okay, what happens from hour 1 to hour 2, and hour 1 to hour 1.5, and hour 1 to 1.1? And they're showing the different calculations there. What they're trying to do when you make this time interval smaller and smaller and smaller, you're trying to find an instantaneous rate of change. And when we talk about velocities and things like that, I mean, an average velocity says, well, on average, I'm traveling, or the temperature is increasing at this. It doesn't mean that at every time point that's how fast it is increasing. Just like if I'm taking a trip and I said, okay, I average 50 miles an hour, does that mean I travel 50 miles an hour the entire time? Chances are not. I mean, there's usually times I need to slow down. There's times I might need to speed up a little bit. There might be times I'm not paying attention and creep up above the speed limit or something like that. So, and that's the difference. I mean, an instantaneous rate of change would say, okay, at this specific time, how fast was I going, or how fast was this temperature actually increasing? Whereas when I'm doing an average, I say, okay, between these 2 time points, on average, that's what I was traveling. At some point, it might have been increasing by that number of degrees, or I might have been traveling at that speed, but it doesn't mean that I was traveling at that speed the entire time, or in this case, that the temperature was increasing at that rate the entire time. So that's the difference between an average and an instantaneous rate of change. Instantaneous rates of change are kind of hard to measure because the whole premise behind that is I'm looking to find the slope of a tangent line. And to kind of go into that, we're not talking about a trigonometric function tangent because we're not going to do trigonometric functions. A tangent line is essentially a line that it intersects a curve, a graph, at only one point. When I do an average rate of change, I'm usually finding the slope of a secant line. I'm taking 2 data points that are on that graph, and I'm basically drawing a line between them and finding the slope of that line. Well, I could do that because I have 2 data points. The problem is if I'm doing an instantaneous rate of change, or I'm trying to find the slope of a tangent line, I only have 1 point of reference, and to calculate a slope, I often need 2. So in this curve here, I have a line that's tangent to this, and the issue I'm going to have with this is that we only have 1 set of coordinates. Therefore, we cannot accurately compute the slope of the tangent line, just based off of that 1 point. So how do we handle that? In mathematics, how do we take care of that circumstance? Well, what we do is we do use the slope of a secant line to approximate the slope. So what I do is I say, okay, well, I'm going to find another point that's h units away from x, where h is some arbitrary distance. I don't want it to be too far away because that would be kind of, obviously it would be quite far off. But I'm just going to say, okay, well, here's my second point of reference, and I'm going to find the slope of this line here. I can visualize the slope. Now I can see that pink line that just got drawn and the red line, which represents the instantaneous rate of change, are not the same thing. They don't even look close to one another. So how do I, get closer to what that tangent line's graph is? What I do now is I say, okay, well, let's make this distance h a little smaller. So now here's where it is, and here if I redraw the line, I can see that the slope still doesn't equal to that of the tangent line, but it certainly is a little bit closer than the previous line before it. So if I make that distance smaller yet, And now it's even closer to x plus h is even closer to x. When I see this line drawn in, I can see I'm getting really close to the tangent line. So basically, as this value of h becomes closer and closer to being nothing, that would allow me to approximate what the actual slope of the tangent line is. So, and that's what we do. We basically take the circumstance, we keep making h smaller and smaller until it basically is equal to practically nothing. And when it reaches that point, then we basically have the slope of the tangent line, or the instantaneous rate of change. And that's how we define that in calculus. The slope of a tangent line to a graph is given to us by the limit as h approaches 0 of, essentially, the difference quotient, something we've studied already. So the average rate of change is given to us by the difference quotient. The instantaneous rate of change is given to us by doing the limit as h approaches 0. So as we can see here, instantaneous rate of change and slope of a tangent line are the same thing. They're interchangeable in our realm of thinking. And you're going to see some questions that will say, okay, find the slope of the tangent line. And or say, okay, find the instantaneous velocity or instantaneous degree temperature change or whatever it is. They all mean the same thing, okay, depending on the circumstance. So finding an instantaneous rate of change in this instance. So I want to find the instantaneous rate of change of the temperature function f of x equals x squared at time x equals 1. So I'm going to set up the difference quotient and set the limit as h approaches 0. So here, h is the variable. X I'm kind of treating, although it is also a variable, it's not the variable I'm focusing my attention on as far as the limit goes. Now, one of the things I want to point out at this point in time, if you were to plug 0 in for all the h's and then evaluate this function, you would end up with f of x minus f of x, so something minus itself, which is 0. And of course, h being 0 on the bottom would be 0, so you would end up with a 0 over 0 circumstance. And that's one of the reasons why we studied that particular indeterminate form, is because when we start doing with slopes of tangent lines or instantaneous rates of change, we end up doing a limit that will oftentimes, because of the way we set it up, give us a difference quotient of 0 over 0 that we have to simplify in some way. So in this case here, one of the ways we can handle that, we know that x equals 1, so I'm going to do the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Again, if I were to plug the 0 in right now, I end up with 0 over 0. So in these cases here, I'm just going to go to the function f of x, replace the x with 1 plus h in the first instance and a 1 in the second instance. 1 plus h squared ends up being 1 plus 2h plus h squared. 1 squared is just 1. And then I'm going to simplify that difference quotient. The reason being, when I simplify that difference quotient, one of the things we had talked about before with difference quotients is that I usually want to work out that difference quotient until, in this case, the h on the bottom would cancel. Well, the reason behind that, the reason why we wanted you to get used to doing that, is that's what's going to allow us to get rid of the indeterminate form and to be able to evaluate this limit. So, that all that stuff we learned before is where it comes into play. So the ones up there cancel. The h's would cancel a bit because I can factor out an h from the top, and then those h's would cancel. So I end up with the limit as h approaches 0 of 2 plus h, and if I plug 0 in for the h at that point, I get 2. So basically, this is telling me that at x equaling 1 hour, the instantaneous rate of change is 2 degrees per hour, which means at that precise moment, the temperature is increasing at 2 degrees per hour. So it's not happening, over the overall course of time. It's happening at that specific moment. If I were to go to x equals 1.5, it might be a little different. So here, you were asked to find an instantaneous rate of change and find a function that represents that. So what's different between this and the example that I went over prior to giving you your question was that you were just asked to find, I mean, we went over a problem where you were asked to find what happened for a single value of x, whereas this is asking us to find what happens at any value of x as far as an instantaneous rate of change. So I'm going to use some notation we're going to define in a moment. I'm going to say, okay, well, I want to figure out what this new function, I'm going to call it f prime of x. I want the limit as h goes to 0 of f of x plus h minus f of x all over h. So I'm going to substitute. I'm going to have 3 times x plus h squared plus 4 times x plus h plus 5 minus f of x, which is just going to be 3x squared plus 4x plus 5 all over h. Now, at any point in here, if I plugged in 0 for the h's, I would end up with 0 over 0. I'll leave that to you to explore that, to verify that, but that's exactly what would happen. So I'm going to go through and try to get this simplification done. So I want this h that's been down here to cancel out, and by canceling out, that's what should make the indeterminate form disappear as well. So if I take 3 times x plus h squared and FOIL that out and distribute appropriately, I'm not going to show all the intermediate steps. If you have any questions about how I got this, certainly come to me during office hours. We go through it a little bit more thoroughly, but hopefully you know how to FOIL and distribute. The 4x plus h becomes 4x plus 4h plus 5. This minus sign gets distributed, so I end up with minus 3x squared minus 4x minus 5 all over h. Now, if you look here, I have a 3x squared here and a minus 3x squared here. They would cancel. I have a plus 4x here and minus 4x here. They would cancel. A plus 5 and a minus 5. They would cancel. So what I would end up with limit as h goes to 0, I'd have 6xh plus 3h squared plus 4h all over h. And of course, the way that the textbook usually shows this, you can use the distributive property, but they're just saying, okay, well, if I factor out the h from the 3 terms on top, I end up with that over h down here. Now, of course, these h's would now cancel because I have a multiplication of h on top and bottom. I mean, down here it's h times 1. We don't usually consider that a multiplication, but it's still there. So now I'm going to do the limit as h goes to 0 of 6x plus 3h plus 4. And now if h becomes 0, I end up with 6x plus 4. So this is the function that would give me any instantaneous rate of change at a specific value of x. So if I knew the value of x I wanted to figure out the instantaneous rate of change at, I just have to plug it into this function down here that I came up with, and I would be able to tell you what the instantaneous rate of change is. This is the premise of what we call a derivative. The derivative, and that's why we use the f prime notation, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So essentially, we learn basically the same thing for that represents three different terms that we used. We said that the slope of a tangent line is the same thing as an instantaneous rate of change, and that's also known as the derivative. And as I said, they will use these three kinds of phrases interchangeably and expect you to know that they are the same thing. So if they say, okay, find the slope of this tangent line, well, that means find the derivative at that particular point. If they say find the instantaneous rate of change at this particular x value, well, again, it means find the derivative or find the slope of the tangent line. All these three things mean the same thing. You're going to see various terminology for derivatives throughout this. We've already looked at the situation where we said, okay, f prime of x represents a derivative. Another way that you often will see it represented is to use Leibniz's notation, and that's d over dx, or we just said something to say d dx. So d dx of f of x is the same thing as me saying f prime of x. So, don't get hung up on the notation. D dx, f prime of x, same thing. That means take a derivative, which again means you're finding the slope of a tangent line. You're finding an instantaneous rate of change. All of them represent the same thing. So, now we focused our attention so far mostly on examples dealing with polynomial type functions, which work really nicely because when you use the difference quotient, you do the simplification process, usually it works itself out. As long as you are foiling and distributing correctly, anything that doesn't have an h in it will eventually cancel out, leaving you only terms with h, which allows the cancelization of the h to occur, and therefore you're able to come up with a function for the derivative pretty easily. There's two other circumstances that you're going to be using a lot, dealing with situations with roots and dealing with situations that are rational functions. And we're going to work through those two circumstances in this example recording. So I'm going to demonstrate the one for you and let you try the other one before I show you how to do that one as well. So again, here's some of the notation. Sometimes you'll actually see y prime instead of f prime of x, same kind of thing, because oftentimes y is used to take the place of f of x, so y prime and f prime of x are the same thing as well. And as I mentioned, d dx are the same thing. And they show here the derivative of x cubed is 3x squared. That could be established using the definition of a derivative we just talked about, that the limit as h approaches 0 definition. As we get further into this particular chapter, we're also going to learn that there are certain rules that act as shortcuts for determining what a derivative is for a particular function as well. And this goes through a more additional notation. Instead of h, they can use delta x. Same kind of thing. The whole idea behind this is that they're trying to show you that all of these things do relate to slope. So anytime we're dealing with these derivatives, we are finding information about a slope. And essentially, derivative is a slope. That's all it is. But that slope represents something specific in each of the cases, depending on what your function is. They're talking about delta notation, So as an example here, let's work through this one here. Say I wanted to find f prime of x using the definition of a derivative for this. So f of x equals the square root of x. So I'm going to use the definition of a derivative, which means I'm going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is my f of x plus h up here. This is my f of x up here. And all I'm doing again in those instances is I'm going to the function f of x. I'm replacing x with x plus h for this one. And this one here, I'm just basically f of x, we know what that is. I'm just substituting at that point. I still want this h down here to eventually cancel, because if I plug 0 in for the h's, I end up with square root x minus square root x on top, which is nothing, 0. I ended up with 0 in the denominator, so I have that 0 over 0 again. I have to simplify this somehow. So how do I do that? Well, in instances where I have roots that are involved, In this case, we usually don't do too much more complicated than the square root. I mean, cube roots would be handled a little differently, fourth roots, etc., etc. What I need to do is I need to figure out a way of getting the numerator to basically be rationalized, which basically means I'm trying to find a way of getting, all of the h in particular, anything that has an h that I could cancel with the one on the bottom, out from underneath the square root symbol. And, most students aren't going to come up with this methodology on their own, which is why, I have to make sure to go through and show it. But what I need to do in order for that to occur is I'm going to multiply the top and bottom by essentially a conjugate. I'm going to have the same two quantities, but the thing that's going to be different is I'm going to have a plus sign between them instead of a minus. The reason being is when I do the foiling process, essentially, I'm going to do the first times the first to get x plus h square rooted times x plus h square rooted, which means I'm squaring a square root at that point. When I do the O and the I part of the foiling process, I'm going to end up with a positive quantity, and then I'm going to end up with a minus of that quantity, so they're going to cancel each other out. And anytime I deal with conjugates, that's what happens. And then when I do the lasts, I'm going to get negative square root x times square root x, which is basically going to make the square root symbol disappear. I do the same thing on the bottom for the only reason that this fraction I'm multiplying to my original, I want it to be 1 because I don't want to change the value of my fraction. I just want to change the numerator so I could make the h in the denominator that I started with eventually cancel with it. So when I carry through the multiplication for this, on top I do end up with x plus h minus x. Now I skipped a few steps there. If you need more to show more detail with that, please make sure you see me in office hours or ask me about it in class. But essentially, I do expect you to be able to FOIL. So, when you do this times this, this times this, this times this, and this times this, I would expect you to end up, once you simplify, with x plus h minus x. In the denominator, I end up with, I just keep it the same, h times the quantity x plus h square rooted plus x square rooted. On top, I have an x and a minus x, which would normally just cancel each other out, so I'm going to do that. And so I end up with h on top, essentially times a 1. I have an h on the bottom being multiplied to that big quantity. Those h's would cancel. And when they cancel, I'm left with the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Everything up here, if I had put the 0 in, again, I would end up with that 0 over 0. Once that h is canceled now, that issue should now be gone. So I'm just going to plug the 0 in for the h. And when I do, I end up with 1 over the square root of x plus the square root of x. And when I add two things that are exactly the same terms, I'm going to end up with 1 over 2 times the square root of x. So that would be f prime of x. So that's how you use the definition of derivative to evaluate a derivative. Now I'm going to ask you to do the same thing with the rational function 1 over x. So for the example that you were asked to try, you were asked to find the derivative of this function here, 1 over x. And I start off the exact same way. I'm going to do limit as h approaches 0 of f of x plus h, which is this part right here, minus f of x all over h. But again, the issue I have with this circumstance is that I'm trying to, eventually get that h on the bottom, which is partially cut off right now, to cancel. So in an instance when I have, things that are being developed from a rational function like 1 over x, what I would look to do is carry through the subtraction on top. And for me to do that, I need to have a common denominator. So I'm going to get a common denominator by multiplying the first fraction by x over x and multiplying the second fraction by x plus h over x plus h. The reason being is I don't want to change the value of those fractions. I just want to get a common denominator so I can carry through the subtraction. So when I carry through those, I end up with x over x plus h minus x plus h over x plus h. Keeping in mind that there are a pair of parentheses understood to be here by the fraction bar. So that minus sign I have here will eventually have to be distributed when I carry through the subtraction itself. So when I carry through that subtraction, now that I have a common denominator, I'm going to end up with x minus h all over x times x plus h. And the only thing you're seeing here is I took this division of h I have right here, and I turned it into a multiplication of 1 over h. The reason being is having a fraction that has other fractions in it can look quite complicated and overly complex, and we try to simplify that issue as quickly as we can. So I do that by basically just trying to get, one fraction times another fraction. So in this case here, in the first one, in the numerator, the x minus x, they essentially cancel each other out. So I have these going away because they subtract out. These, I have a negative h on top and a positive h on the bottom, kind of going back to some rules of simplification you learned way back when. Now there's a negative here, so it's a negative 1. This is a 1 here. So on top I'm left with negative 1. On the bottom I'm left with just x plus h times x. Now, everywhere along here, if I had plugged in the h approaching 0, if I put the 0 in, I end up with that 0 over 0. Now that the h's have canceled, now I plug that 0 back in, I end up with negative 1 over x times x, which is the same thing as negative 1 over x squared, or I can write that as negative x to the negative 2 power. There should be a negative here. It didn't come through for whatever reason. There should be a negative there. So that's how that would be the derivative of the function f of x equaling 1 over x.